We are standing right at the precipice of a computational revolution. I mean, this is a technological moment that promises to reshape, well, basically everything from drug discovery to climate modeling.
Exactly. The potential of quantum computing it's just huge,
Yeah.
especially for these really complex fields like material science and chemistry.
And it feels like we're moving faster and faster towards this era of what's called fault-tolerant quantum computing, right? FTQC.
Right. FTQC is the big milestone. It's the long game.
So what is that exactly?
It's the point where these machines become stable enough and scalable enough to solve problems without being constantly derailed by, environmental noise.
And when we get that point,
When we cross that threshold, the applications will be completely transformational, especially for advanced economies.
okay, let's unpack that. If this immense quantum power is coming, and it's going to shift the global balance of tech, then the biggest challenge isn't the physics anymore.
No, it's a governance challenge.
It's about equity. Who gets to use this power? Because from what the research shows, we are staring down the barrel of a rapidly widening quantum divide.
That's the core issue, really. All the access, the infrastructure, the resources, they're getting heavily concentrated, which just reinforces the inequalities we already have.
So for this deep dive, our mission is to look at those structural barriers, the things that are basically creating a quantum version of the digital divide.
Yes, and crucially, we also need to highlight the proactive solutions, the things being designed to make sure quantum tech serves the common good, globally, not just a select few.
To really get a handle on this divide, I guess we have to start by following the money. That's where the story of concentration really begins.
And the numbers they're staggering. As of mid-2024, nations have committed something like a colossal $40 billion to quantum R&D.
$40 billion.
Yep. And that covers the whole spectrum: computing, sensing, communication. It sounds like this massive global effort.
But when you actually look at the investment map, how global is it really?
It looks less like a globe and more like a few intense spotlights. The vast, vast majority of that spending is heavily concentrated in North America, Europe.
Right, with big initiatives like the EU Quantum Flagship.
Exactly. That was over $1 billion. And then, of course, the Asia-Pacific region.
So we're really talking about a handful of countries making huge strategic bets on this.
Oh, absolutely. These are multi-billion-dollar national missions. China, for instance, has committed around $15.3 billion. Japan is up there, too, with nearly $8 billion.
And how does that compare to what we see in the Global South?
It's not even a comparison. The data is often sparse, and the figures we do have are just tiny fractions of that.
So the magnitude of the difference is the real story.
It creates this massive funding asymmetry. I mean, to put it in perspective for you, South Africa is listed at about $10.7 million, Brazil, $16 million, Qatar, $10 million.
You put those numbers next to 15 billion.
Right. It means for most of the world, quantum power isn't a promise. It's becoming a structural barrier that's being built right now, today.
What's fascinating here is that this isn't just a money gap. It creates what the sources call an opportunity bias.
Yes, that's a perfect way to put it.
If all the research is happening in places with huge financial sectors or big pharma or high-tech car manufacturing,
then the R&D is going to focus on the needs of those industries. It just is. Innovation gets pointed toward maximizing profit or optimizing supply chains.
and that completely overshadows the big global challenges, like the UN's Sustainable Development Goals,
Yeah.
the SDGs.
Exactly. Things that disproportionately affect the very regions that are being underserved by quantum. So the people who need climate and health solutions the most are being shut out of the R&D cycle from the very beginning.
Okay, that makes the challenge really clear. So beyond the investment map, what are the hard structural barriers? Like the infrastructure, the people, the policies that are stopping countries from building this capability themselves?
Well, the first and most obvious one is the infrastructure deficit. It's a hard barrier, and we have some pretty striking findings on this from a UNESCO global survey.
What did it find?
Almost a third of the people they surveyed, so 31.9%, said their institutions have zero quantum facilities. None.
Wow. Not even the basics.
No dilution refrigerators, no specialized optics labs, nothing.
But the common argument is that cloud access should fix this, right? You don't need the multi-million-dollar machine in your basement. You can just log in remotely. Is that not leveling the playing field?
It should be, but the data just doesn't back that up. Even with cloud access, over 21% of respondents still said they were unable to access the necessary facilities.
Why? What's the problem?
Well, there are a few things. Technical issues like high latency can make running complex experiments almost impossible. Time zones make sharing resources a nightmare. And, I mean, let's be honest, commercial providers are going to prioritize their big 10 clients
Yeah.
who are in those advanced economies. So researchers in developing nations get pushed to the back of the line.
Precisely. So even digital access ends up creating this technological dependency trap. Your research is totally reliant on foreign infrastructure, and you have almost no control over it, which stifles any chance of a local quantum ecosystem ever emerging.
Yes.
And I have to imagine, if you can't build the labs, you certainly can't keep the people. It sounds like a vicious cycle.
It is. If you concentrate the investment and labs in a few places, you create a vacuum of expertise everywhere else. This brain drain is happening, and it's happening fast.
How bad is it?
It's an acute crisis. The survey found only 16% of countries reported a net inflow of quantum talent,
60%.
which means a staggering 84% are either stagnating or actively losing their experts. They're failing to hold on to the very people they've invested in training.
And I bet those researchers are pretty clear on why they're leaving.
Oh, very. The top reasons they cite are inadequate funding for the long term and just unstable career paths. And those problems are, of course, way worse in underserved countries that just can't offer a viable career at home.
So they train these brilliant minds and then just watch them leave for better resourced labs abroad.
That's the story.
And there's another layer to this talent problem, isn't there? The gender disparity.
A deep one. The entire survey population was only about 27% female. It's a huge signal that the community is failing to attract and, maybe more importantly, retain half of the world's potential talent.
And the reasons cited go beyond just education.
Right. The barriers women mentioned are about a lack of visible role models, a sort of cultural inertia in the field, and difficulties with work-life balance. So the problem is institutional, it's cultural, and it needs high-level policy to fix it.
Okay, so that's a perfect transition to the third barrier, policy deficits. You mentioned these dedicated national quantum strategies, or NQS. Why are they so important?
And NQS is basically a country's blueprint for its quantum future. The US, China, the UK, Germany, they all have one.
And that gives them a foundation.
It gives them a political foundation for sustained funding, for talent programs, for connecting quantum tech to bigger national goals.
And on the other side,
Most countries in sub-Saharan Africa, large parts of Latin America, and much of Asia just don't have one. And without that top-level commitment, it's basically impossible to get the resources you need or create the stable careers that stop the brain drain.
so what did the people in the field say they needed most?
No surprise here. They universally cited more research funding and, of course, infrastructure development as the two most urgent policy needs.
So we're facing this triple-layered divide. Concentrated money, no labs, and vanishing talent. The sources suggest there's a shift happening, though, moving from just talking about the problem to actually doing something.
Yes, moving towards something called anticipatory governance. And that shift is probably best embodied by the Open Quantum Institute, or OQI.
OQI. And that came out of GSD in Geneva, right? Hosted at CERN.
That's the one. It's designed to be this novel science diplomacy instrument. Its whole purpose is to bridge this exact divide we're talking about.
So OQI is this neutral, multilateral platform for sharing the tech fairly. And they have a mission built on 4 pillars, I see.
That's right. First is accelerating applications for humanity, so a direct focus on the SDGs. Second is access for all, which tackles that infrastructure problem head-on by providing cloud access.
What are the other 2?
Third is advancing capacity building, and fourth is activating multilateral governance to help shape global standards.
Let's zoom in on that capacity building piece. That seems like the most direct way to fight the brain drain. How do they do it without just telling everyone to move to Geneva?
They're really focused on hands-on skill development through things like hackathons and very focused training programs, and we have some concrete data on this. OQI has supported over 380 participants and handed out more than 320 certificates through a partnership with an organization called Q World.
Okay, but what makes this different from any other technical training program?
The key is where they hold them. These events are strategically held in quantum underserved regions. The goal isn't just to teach a bit of code.
It's to build a local community.
Exactly. It's to create new local and regional quantum hubs, to build a critical mass of people and create an ecosystem that can actually sustain itself. That's how you mitigate the talent drain.
So they're seeding the expertise right where the need is highest. But wait, if they're only focusing on these non-commercial SDG-type goals, isn't there a risk they could scare off the big industry players? I mean, they need their hardware to make this work.
That is a really valid question. It gets to the heart of this balancing act. The way OQI addresses this is by making sure its teams are incredibly multidisciplinary.
What does that mean in practice?
It means they require every team to have quantum experts, classical computing experts, domain experts who know the specific problem inside and out, and this is critical impact experts who understand the relevant SDGs.
So the science is being guided by the social need, not just the corporate bottom line.
Precisely. And they have this structured process, 5 phases from the initial idea all the way to actually running it on a quantum computer, that ensures they stay focused on these high-impact areas.
What's so clever about this is how it connects two worlds that rarely intersect.
That's it. These underserved regions might not have quantum PhDs, but they have incredible domain expertise in the challenges they face every single day.
Water scarcity, food security, disease management.
All of it. OQI's job is to connect that on-the-ground knowledge with the cutting-edge quantum tools needed to tackle it.
Which makes the science instantly relevant.
Yeah.
Okay, give us some real-world examples. What do these SDG-aligned projects actually look like?
Let's start with a huge one. SDG 6, clean water. They're working with Unhabitat to figure out how to optimally place sensors in big urban water networks to detect leaks.
Which is a massive source of water loss in growing cities.
Massive source.
Yeah.
They're also using quantum modeling to better understand groundwater resources and how climate change is affecting them.
And these are problems that classical computers really struggle with. What about health? SDG 3.
For health and well-being, some teams are using quantum machine learning to speed up the discovery of new antibiotics. That's a huge deal with antimicrobial resistance on the rise.
Okay. And climate. SDG 13, climate action.
There we see work with groups like the European Weather Forecasting Center to make climate models more reliable. Better forecasting is essential for vulnerable regions. Other teams are using quantum simulation to try and improve the efficiency of carbon capture.
Right, directly targeting CO2 in the atmosphere. And the absolute key to all of this, the thing that makes it possible, is getting access to the hardware.
That's the essential link. The OQI access pillar is what makes this real.
How does it work?
OQI secures access to state-of-the-art quantum devices through donated cloud credits from the big quantum providers.
So research teams from anywhere can actually run their experiments without facing that crippling cost barrier.
It's what turns theory into a real-world implementation.
So, to wrap up what we've deep dived into, the quantum divide is real, and it's getting wider. It's driven by this huge $40 billion concentration of investment, a massive infrastructure gap, and a really damaging brain drain.
But these proactive models, like OQI, they offer a real path forward. They do it through targeted skill building, like those hackathons, and by focusing rigorously on these high-impact SDG use cases.
And the sources are clear that this can't just be a short-term project.
No, absolutely not. The road ahead needs sustained multi-stakeholder commitment from governments, from industry, from academia. These programs have to be sustainable well beyond their initial phases around 2026.
So when you pull it all together, what does this all mean? We usually frame quantum development as this zero-sum race for national or corporate power. But the core insight here seems to be that building a globally inclusive quantum ecosystem isn't just, a nice thing to do. It's not just about fairness.
It's a strategic imperative. The full transformative potential of this revolution, its ability to solve our biggest global problems in climate, health, and food, can only be unlocked when all perspectives are at the table.
Especially the perspectives of those who are most affected by these crises.
Yeah.
Exactly. If you don't include the world, you limit the physics. And you limit the solutions that, frankly, we all desperately need.